Okay, so first off, hopefully you all got my public service announcement. I'm going to push back the relative humidity lab by a week. I did finally get through all of the lab ones, and I would put it in literary terms. They were the best of times, they were the worst of times. Okay. Some of you guys nailed it, crushed it, knocked it out of the park. Some of you, yeah, not so much. Okay? Guys, I know, I always hear people say, you know, I'm an engineer. I don't have to know how to write. Let me explain something to you. Okay? This is not my little fetish. I never imagined myself as a teacher. My goal when I was in your chairs was to be a principal program manager at Boeing. Back when Boeing was a good company. That's another story. Okay? In your lives, the one thing that all of you are going to do is sell stuff. Okay? And that's whether you sell your idea for a new product to your manager, whether you try to sell some pretty guy or girl on a date, you're always going to be selling stuff. And you must be clear and convincing. Okay? And that's what good writing is all about. So, let me just say that when I read something, I should be able to start at the beginning. I should have a topic sentence. I should know exactly where I'm going to be going through this paragraph. I should see a bunch of supporting statements. And when I get to the bottom, it should be nice and neatly wrapped up with, you know, some kind of a closing statement that says, you know, here's the results, here's why the topic sentence was good to go, something like that. Okay? It should not be, here's the answer, and you know, there's some calculations over here that support it, and I gotta go look for it. And look, let me explain something to you. If I was your principal engineer, and we were at Pratt & Whitney, and we're doing the redesign on the F-135 engine, and we go to a formal design review with the product fellows, and you guys did something like that, your career would be short, sweet, and over. Okay? You would be out in the next round of layoffs. Okay? You gotta, when you're writing something, imagine your audience has almost no idea what you're talking about. Because generally your managers are going to be clueless. I can tell you, I had lots of them. All right? So clearly, state the problem, state where you're going, support it, close it out. Do not make the readers search around. Don't make them have to draw their own conclusions from, you know, a picture over here, a calculation over here. Guys, this is critical stuff. It is absolutely important that you get good at decent writing. All right? All right, enough harping. Please follow the sample report that I gave you. So I do not want to see any questions just copied into the calculation section, and then a bunch of math, which may or may not be right, and then the answer. Okay, I'm really going to crush you on the next one if I see it. What I want to see, you got a question. Write a topic sentence for how you're going to answer it. Put in all your equations and stuff and how you're going to go about it. You know, maybe you're going to invoke the first law, the second law of thermodynamics, something like that. Cool, great. Do your math. Some of you would have been helped by just breaking the math down a little bit. You tried to do a bunch of algebra and combine a bunch of equations and terms, and you know the math didn't work out. You got the wrong number. If you got to do several steps, cool, that's fine. You know, just say, okay, we're going to start by calculating the energy rise over a certain period of time, and then get that number. Great. Okay, now I need the power, so I'm going to divide by time. Great, cool. Do that, get the answer. And then at the very end, wrap it all up, support that topic set. All right. So, show of hands, I'll let you guys vote. Do you want me to just go into MEE365 365 email account and just delete all of the relative humidity labs? Let you guys send them in again? Okay, show of hands. Who says, yes, I want just everything deleted for lab 2? Who is against that? I got one against, I got a whole bunch for. Okay, so what I'm going to do, I'm going to go into MEE365. I'm going to delete all of the relative humidity labs like they never ever existed. Please send it to me again with whatever changes you want. As soon as I start seeing them start appearing in the 365 email account, I'll begin grading them because it shouldn't have dragged on as long as it did. You know, I basically had to get calibrated to know how long is it going to take. So I will do my best to do a whole bunch this weekend. If you think your stuff is good to go, and I will get you grades back. This is a writing intensive course, so if you got crucified on the first lab, don't worry about it. You're going to be able to do a rewrite on one lab with the feedback. Okay? So that'll probably be the last lab submission you do for me. And then I got to figure out if I can probably just average everything together. So you can pull this out. Okay, subject matter of the day. We have a new lab coming up, which will be lab 3. It's going to be this thing. And we're going to talk about propulsion efficiency. I will publish the pre-lab questions. Basically, the lab is going to be, I want you to make a Newton of thrust. And you're going to do it with 3 different propellers. And you're going to measure the power input, which you'll be able to see on the power supply. So when I turn that on, you got the amperage going into the motor, you got the voltage going into the motor. You can calculate the power in. You are going to have to write another piece of code. You're going to take that MEE365 template I gave you and take the tachometer program that's in the Lesson 7 folder. I want you to merge those two together so that you have RPM of the propeller coming out the data streamer. Okay, shouldn't be too hard. You don't have to really create any software. Okay, but you got to do some cutting and pasting and you got to debug it. I think that's fair, the amount of coding that you're going to do. You are also going to have to read 2 analog inputs. So not only will you get RPM, which is going to come out of that. Maybe you can yeah, it's not sure. Anyway, right here, there's a little electric eye called a phototransistor. It's a very fast switching switch. And we're going to shine a cool little laser into that electric eye. When the beam breaks, it's going to give you a signal that's proportional to RPM. Then you're going to read the load cell up here. Load cell up there. That's going to give you the running torque that's coming out of that motor. And you're going to have to read this load cell right here, which will give you the thrust. So you're going to be able to calculate the power going into the motor. You're going to be able to calculate the shaft work coming out of the motor. You'll be able to look at the motor efficiency. And then you'll be able to compare the power it took to make the thrust, theoretically, from just accelerating the airflow through the rotor disc to the torque and speed coming out of the motor that's actually creating the thrust. It'll be clear once I write it all out, but that's where you're going with this next lab. So we're going to look at thrust-specific propulsion. You know, how much power do I have to put in to make a Newton of thrust? And as a byproduct, you're going to get some cool understanding of, you know, how do I make an electric motor run efficiently? They're very cool. So electric motors have your maximum torque at 0 speed, which is why electric cars are pretty spunky at low end. Okay, that's also a really horrible place to be running, and you're going to see why in this lab. So if you get into any kind of electric vehicle program, anything like that, hopefully you'll harken back to this, and you'll understand how to make a nice, efficient design. So that's what's coming up for the next lab, once you get your relative humidity labs back in. Okay, so let's talk about this cool business of how you're going to measure the RPM of that propeller. Okay, it's not super hard, but it's not trivial. First thing we got to do, we got to measure time. Okay, you did that in the last lab. You got time equals millis. So if I do the millis command right there, I get a number that's the number of milliseconds that the program's been operating. Cool. We saw that, we've been there, we've done that. Time has to be an unsigned long data type, 32-bit number, and it can be anything from 0 to this 4.3 billion trillion. Whatever this big number is right here. It's 2 to the 32nd power. If you had something that was really long, like you're measuring, I don't know, tide cycles or something for a month, okay, that's going to roll over after about 50 days. So when it hits that 4.3 billion, trillion, quadrillion, okay, it's just going to roll over to 0 and start over again. Just keep doing that. Okay? That is not going to work for this. This is just way too fast. Milliseconds is not enough resolution. So, for the fast stuff, we use micros, which, just like millis, returns the number of microseconds that the program has been operating. So you will want a micros command in your RPM measuring. It's a lot faster. It's 1,000 times faster. So it's going to roll over its unsigned long in about 70 minutes. Hopefully, you guys will be in and out of the lab in 70 minutes, and that won't be an issue. But if you had something really long, and you had to measure and time it precisely, you've got to know that that could be a thing. So, there's two things we could do. We could tell the Arduino, hey, go look at the input pin and tell me if you see 5 volts or not. And, we could put that in void loop. And every time we go through void loop, they'll look at the pin and say, you're high, you're low. You're high, you're low. Okay, that's really easy. It's pretty robust. It's also fraught with peril. So you could just do this. That's the command you could actually use if you wanted to do polling. Remember, if you're going to do a conditional, you got to have the double equals. If you put a single equals here, you're going to set digital read 3 high, and this will always be true. Okay, so don't fall into that trap. I would encourage you to start this program early. If you guys want me to leave out one of these units that you can play with so that you can debug your software, I'm totally good with that. I could leave one in the dry lab, whatever you guys want. Okay? So you can just say, if the pin goes high, record the time, and I can maybe get 1 or 2 times, look at the difference between them. The delta time might be interesting for how long it took for the blade to go around. You can do that. There's a problem. How do I know that the blade wasn't going around so fast that I missed it, and it's already come back around again? I have no to know that. Okay? You could, in some ways, if you could sample like 10 times faster than the fastest event you want to look at, you might be able to pull that off. Okay? But it's really dicey. Really, really dicey. I would never do that. The better way to do that for timing an event and knowing you didn't ever miss it is something called interrupts. Okay, so an interrupt is an event that causes the microcontroller to just drop everything. And it runs over and it services a predetermined interrupt service routine. Okay? So you are guaranteed you will never, ever, ever miss that event. You can have some other issues, but you're not going to miss the event. This is critical when we do things like read an encoder. So if I want to measure the shaft speed of something going around, maybe I'm back at Heidelberg Web Press, and I want to measure the rotational speed of my printing press. There were encoders all over that machine. And they were constantly monitoring the rotation position of those printing press rolls. There are all kinds of different interrupts. Guys, we're going to do just the baby, simplest thing you could ever imagine. Okay? But, just so you know what's out there, typical interrupts are a pin changing state. So right now I've got pin 2 wired to an electric eye, and every time that eye becomes non-conductive, it says, oh, okay, something happens, and it goes off and measures the time. You can have a timer register rollover. So for example, if micros roll over, you can write a piece of code that will say, okay, micros rolled over, I better go service that. Maybe I want to count the number of micros rollovers that happen. You know, I got to accurately measure something longer than 70 minutes. You can do that. That's totally legit. A serial communication message coming in, you know, maybe, I don't know, I send a serial signal to the microcontroller that, hey, you got to deploy the airbag because an oak tree is coming up the hood at me. So that might be something you want to service right now, right now. And lastly, a data buffer filling up, which is almost the same thing as a serial communication message. But again, all we're going to do is we're going to look at a switch firing. That's it. Super simple. And even that, I'm going to give you the code for it. Okay, already told you that. So just so you know what's going on, the easiest way to deal with an interrupt is something called an input pull-up. Okay? This is my Arduino chip. Inside the chip, I can say, you know, make D2, digital pin 2, make it an input, make it something I can read. And I can say input pull-up as one of the parameters. And what it does inside is it hooks up 5 volts to a 20K resistor, ties it to the pin. Now the pin is always going to be high if it's just like, you know, in its free state. And then when I close this switch, D2 gets grounded, goes to 0, and I have a signal that I can then measure or time or do something with. Okay, let's take a look at how that works. So the actual code, and this is in the folder for this lesson. So this is the code that's actually running in this right now. So the usual thing, I have a header, I describe what the code is doing. I have a pin connection, so I've got D2 hooked to a photo transistor going to ground. That's just this, that's just the switch. So it's either conductive or not conductive, so I can get a signal. I declared a bunch of variables. void setup. Okay, here's that input pull-up. Right there. So pin 2, input pull-up, do this. That's what it's saying. And then you have to say attach interrupt. Guys, just copy that. I struggled and struggled to get that right this summer. There's all kinds of ways you can do it wrong. You could say attach interrupt 0 to pin ISR. Okay, pin ISR is the interrupt service routine. That's a subroutine that's going to run. And do it just when the voltage is rising. So when it's transitioning from 0 to 5 volts, that's the only time it can fire the interrupt. Your options are rising, falling, or both. But I only went with rising so that when the blade is passing out of the electric eye, then it fires. Now here, serial begin, establish communication to send data back to the PC. And then I've got an old micros and a new micros. So basically, I've got two 32-bit numbers, and if I take the difference, I've got the duration between when the blade went around. Well, I've got the duration for when it goes 180 degrees, because I got 2 blades. When you do the interrupt service routine, so whenever the interrupt fires, it's going to come down here and do this little subroutine right here. You want to keep those short. Do not put math in there. Generally, I just put a flag in there that says, hey, something happened. And then I come back up to the main routine. So interrupt occurred, I set that to true. And I come back to my main loop. If interrupt occurred equals true, then do a bunch of stuff. That may seem like a really convoluted way to do things, but it's going to save you a whole lot of pain. So what it does is it writes down the new micros time. If new micros is greater than old micros, compute the elapsed time, do a bunch of math to get the RPM. So that's just converting microseconds to RPMs. I've got 2 blades, so I have to divide RPM by 2. And then serial print, send RPM and the value back to the screen. I'm going to set old micros equal to the current micros and turn off the interrupt occurred flag so that it can just sit there. Normally, void loop is just going to go round and around and around and around and around, doing nothing. Okay. As long as interrupt occurred is false, nothing happens. The chip just sits there and waits for the next interrupt to happen. And then when it does happen, bam, it's serviced in the main loop. Okay. It's probably going to be a little bit fuzzy until you try it for the first time. Once you try it, it's pretty obvious. Okay, so this sets everything up. That is all there is to the program. So you're going to merge this into the 365 template and send RPM out to the screen so that data logger can grab it, along with the 2 load cells. So when I actually fire this thing, take my little laser pointer. Yep, you can see. So every time the beam breaks, it fires the interrupt service routine. I assure you that's not going 18,000 RPM. average, you'll be good to go. Okay, so that pretty much covers measuring the speed of the shaft, measuring the propeller speed. Okay, when it comes to measuring the thrust, excuse me, the torque of the motor, you're going to use a load cell. And these things have 4 little wires coming out. You guys should remember from Mech Lab 1, remember all that strain gauge stuff that Professor Pudsey's probably talking about? Didn't take Mech Lab 1? What's that? Oh, okay. Okay, let me rephrase the question. You guys know what strain gauges are? I say yes. I see a bunch of people that need coffee. I see a no. All right. Strain gauge. It is nothing more than a stretch sensor. And then I'll put this in the lecture for next time. So what you have is a little piece of polyamide plastic. Looks like this. And you photo etch a bunch of wires that are super, super fine. Looks like this. There's a little solder pad right here. Solder pad right here. You glue this onto a piece of metal, and then when the metal gets stressed, it either stretches or compresses. When it stretches, the internal resistance of this goes up. That's because the little lines become narrower, it's harder to pass the electricity, the resistivity goes up, and so you get differing resistance. Same thing, well, just the opposite when you compress it. When you compress this strain gauge, the little lines in there get wider, become more conductive, the resistance goes down. Cool. These things are a pain in the butt to put on. You got to glue them on, you got to solder these teeny tiny little pads. They're just not fun. You want to avoid it if at all costs, or if at all possible. All right. If I take this thing, however, this has the strain gauges all industrially applied. So they're in there, they're potted under this white plastic, and you just got to read them. So no soldering, no nothing, good to go. You guys are going to have some fun with this because, excuse me, next semester, when we do 375 together, you're going to glue on some strain gauges onto a soda can. You're going to hook up an amplifier, and you're going to tell me what the pressure is in a soda can using the thin wall pressure vessel equations. But that's for another day. So, if I take this thing and I try to bend it, I will get some varying output because my strain gauges are arranged in this kind of arrangement. So these are my strain gauges. I'm going to put power on the top rail, ground on the bottom rail, and I measure from this center connection right here. This voltage divider gives me one output. This voltage divider gives me a different output. And then I measure the difference between output 1 and 2. There's a problem. It's generally a really, really small voltage. Okay, so if I've got 2.5 volts here, I've got roughly 1.5 volts right here. Excuse me, 1.25 volts. These are typically in the range of 350 ohm. if I really grab onto this thing and I just bend for all I'm worth, maybe I can get this up to like 1.26 volts, maybe if I'm really reefing on this thing. Okay. That's hard for a little microprocessor to deal with. So we put amplifiers on it. Now, I was nice to you guys. I know that may be hard to believe. When I was in school back in the papyrus days, we actually had to sit there and wire up our own little op-amp chip. And it was a horrible lab. I hated that lab. So what I did all the wiring for you. This little board right here, that's got the amplifier chip. You just have to run, the load cell leads into it, power, ground, and send the analog voltage back to the Arduino. And then, by changing the gain on the amplifier, you can make this load cell more or less sensitive, and you can read it in the range of 0 to 1023. A whole lot easier. Okay? So you can amp this thing up to the point that I've actually been able to use this as an accelerometer, so I can measure it sagging under its own weight when I go from vertical to horizontal. Okay, that was a highly caffeinated sensor. But it does work. You can do it. You're not going to be nearly that high. I'm also going to give you the gain equation for the amplifier. The manufacturer puts out some numbers and you just have to plug in the gain resistor, you'll get the gain factor. So if this is like maybe 0.01 volts, maybe we gain it up by a factor of 1,000. Well, actually, make it more realistic. 0.01 volts is the difference between these two. We gain it up by 1,000. Now you'll see a difference of 1 volt coming out. Okay, that's nice and easy for the microcontroller to deal with. And that's what we're going to be doing to measure the thrust loads and the torque loads. You will have to do a calibration, so I'm going to give you some weights and a nice little piece of string. So you will hang some weights over here, the string will pull back, the weights will pull down, the little roller wheel. We'll get into all that. Okay. So you'll have to make a calibration curve, and then you'll be able to measure bits to actual force. And that will all be in the write-up that is coming. All right, again, short lecture.